Now, the good news is I have two easy ways of finding those where we don't have to necessarily do them by hand. We can use Maple, and we can use Wolfram Alpha. So let's write down in our notes how we do that. Let's just say, for example, I'll come over here to the side and write a matrix 1, 2, 3, 4. If I wanted to find the eigenvalues of that matrix and their corresponding eigenvectors in Maple, what I do is, before I do anything, I make sure I load the linear algebra toolbox. Then I type in my matrix, A colon equals, and then it's two brackets. Actually, first it's the word matrix capitalized, parentheses, two brackets. Put the first row in there, 1, 2. Close the first bracket, comma, bracket 3, 4, bracket, close. Then you can use either the right-clicking contextual menu to pull up and select eigenvalues, eigenvectors, or you can just type in, capitalized, eigenvector, parentheses, A. That will give you the eigenvalues and their corresponding eigenvectors. If you do just eigenvalues, it actually just returns the eigenvalues. But for our purposes, we want to know what the solutions, that is, the actual eigenvectors are as well. In Wolfram Alpha, you can just go in and type eigenvalues. And then the way that they suggest to do it in the help menu for Wolfram Alpha, you can use brackets the same way I did here. They actually use curly braces. 1, 2, close curly brace, comma, open curly brace, 3, 4. Now, as it turns out, the reason I actually like Wolfram Alpha a little bit better in this context than Maple, although in general I like Maple better, is there's something we're going to do in 8.2 that needs something called a generalized eigenvector, which are kind of clumsy to do in Maple, but Wolfram Alpha tends to just return them to you directly. As we get to it, you'll see why it's nice to be able to have that calculate automatically for you. But I wanted to have you put this in your notes so you can refer back to us. Again, the nice thing about Wolfram Alpha, too, is that it's available everywhere, so you can actually pull up the Wolfram Alpha app or go to your browser on your phone and even have it right there handy. Now, of course, there are other ways to do this. If you've got a... I'm not sure if the CX version, but if you've got like a computer algebra system, a CAS... like a TI calculator, the TI-92, the TI-89, or the TI-Inspire. Those calculators also will do eigenvalues and eigenvectors if you can figure out how to make them do that. The point is, I don't want you to waste your time calculating eigenvalues and eigenvectors because you're going to have enough to do once you know what they are. Okay? They're the key to the solutions to these systems, but there's still enough different cases that you've got to remember what to do with them, and there's a little bit of work to be done.
Doesn't Wolfram, they accept the MATLAB version too, which is just...
Like if you put the brackets in there, I mean, Wolfram Alpha is a natural processing language, so it's going to try to decipher whatever you put in there. So you can use different variations of notation, and sometimes it will still work. Like, for example, earlier today, I was in Maple, and I typed EIGNE vectors, and it just gave me an error. I typed the exact same thing in Wolfram Alpha, and it's like, did you mean eigenvectors? It's like, yes, I did. So, you know, it's nice in that it's doing that behind the scenes for you.
The bracket 1 space 2 comma 3 space 4 bracket.
Yep. In fact, if you don't even type the word eigenvalues and you just put in a matrix, it's going to guess what do you want to know about this particular matrix, and it depends on the matrix as to what it gives you back. Because sometimes, if it's like all ones and zeros, it thinks of it as a special kind of matrix. What do we call those? It's part of graph theory. It's an edge. I forget what the name of it is in graph theory, but it thinks of it as a specific type of matrix and then returns things specifically to type of matrix, but it still gives you all the other stuff if it was just a generic real matrix. Okay, with that said, let's start talking about now how we solve the systems once we know those things. We've done this a little bit, but now we're going to explicitly walk through all the different scenarios. So let's start with an example. Let's say, yes, sir?
I'm recording this.
Yes, it is recording. I started right after this up here, so it's all on there. All right, now x prime is 1, 3, 5, 3 times x. There's your homogeneous linear system. It's homogeneous because there's no term over here, no other vector that depends only on the t. Now this, you'll notice, actually has no t's in it, so it's what's called an autonomous system. But you're thinking of x, capital X, as a function of t, right? Which would be like an x1 of t and maybe an x2 of t. So technically this system is equivalent to saying dx dt is x1 plus 3x2, sorry, and then that's x1, x2 dt is 5x1 plus 3x2. But now I've just written it in matrix form, okay? Now what we learned by example in 8.1 is that once I saw that the eigenvalues and eigenvectors were part of the solution, I can immediately write down a solution. Okay, give me just a second. I'll come right back to this page, but I'm going to jump back to where we were when we saw that. What I did in 8.1 was I gave you a problem like this, and then I said, here are the two solutions. Verify that they're solutions. Now we're talking about where did these come from. Okay? And I talked about it down here. It came from this Eigen equation, namely that this -2 up here was an eigenvalue, and the 1, -1 was its corresponding eigenvector. And 6 was an eigenvalue, and 3, 5 was an eigenvector. Just so happens there's the exact same one that now we're going to see where it comes from. So let's go to Wolfram Alpha. And I'm just going to type it in so you see what it looks like. But I'm just going to do eigenvalues. What was it? 1, 3. And 5, 3. Okay. So lambda 1 is 6, and its corresponding eigenvector, is 3, 5. Lambda 2 is -2, with v1 is -1, 1. Okay? So I'll just go jot that down. Using Wolfram Alpha, I get that lambda 1 was 6, and v1 was 3, 5. And lambda 2 is -2, and v2 is 1, -1, which means I can immediately write down the linearly independent solutions to this system, right? x1, the first solution is 3, 5, e to the 6t. And x2 would be 1, -1, e to the -2t. Those are linearly independent solutions. And so I would write my final solution, my general solution, as a linear combination of those. Namely, x is C1, x1, 3, 5 e to the 6t plus c2 x2, which is 1, negative 1, e to the negative 2t. So this is one form of the solution. Or, thinking again of xt as x1, x2, then if you just were to multiply out this vector here, you get that x1 of t, the solution to the first dependent variable, would be 3c1 e to the 6t plus c2 e to the minus 2t. And x2 of t would be 5c1 e to the 6t minus c2 e to the negative 2t. That's just another form of the solution. So that's the simplest of all cases. It's simple because you've got two distinct eigenvalues. They're both real, and they both have one corresponding eigenvector. Or another way of saying that is the eigenspace that goes with this eigenvalue is just one-dimensional, right? Any scalar multiple of v1 is also an eigenvector that goes with lambda equals 6. That's one of the things we learned in linear algebra, is that if you get an eigenvector, then any scale of it is also an eigenvector. If you get two eigenvectors, then any combination of those is still an eigenvector for that eigenvalue. Okay. So I'm going to go ahead and write it down as a theorem. Let's explicitly state this, that if I get distinct eigenvalues with eigenvectors, then I can write down the solution immediately. So this is the best of all possible cases, 8.2.1 in your book. Okay, this is the general solution of the homogeneous system. And again, I'm thinking of x prime equals ax. That's the system we're talking about. Let lambda 1, lambda 2, all the way out to lambda n be n distinct real eigenvalues of A. So already we're very restrictive, and we're only talking about that possible scenario, distinct and real. A being an n by n matrix, if we get all distinct eigenvalues, and then we're going to let, let's do V1, V2, all the way out to Vn be the corresponding eigenvectors. So V1 goes with lambda 1, V2 goes with lambda 2, all the way up to Vn goes with lambda n. Okay? In other words, A Vi equals lambda I Vi. That's what it means to be the corresponding eigenvector. Then, the general solution is capital X C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t plus Cn Vn e to the lambda n t. Which is just a formal statement of what I just did. Okay, so let's try one on your own. I'm going to just give you a system. I'm going to unlock your computers. I want you to go in and grab the eigenvalues from Maple, or from Wolfram Alpha and give me the solution. Okay? I'm going to stop broadcasting in 3, 2, 1. All right, go back up here. Here's the problem. dx dt is 2x plus 3y, and dy dt is 2x plus y. Go find me the solution. Oh, I paused that whenever I stopped the problem up here. So the answer you guys got. Everybody agree with this one right here? X is C1, 3, 2, e to the 4t. C2, negative 1, 1, e to the negative t. See where that came from? Okay. So we're going to do this example now. The only change is it's now 3 by 3, right? You've got 3 variables, 3 dependent variables. So you just got to find the eigenvalues and corresponding eigenvectors, which will be in R3 now. So go shoot that into Maple and see, or in Wolfram Alpha, see what you get. Come on, it's not that hard. I'd be done by now. Did yours take a while? How embarrassing for it. 5, negative 4, negative 3, 181, 10, negative 1, 1, 101. Beautiful. So, final answer, x is C1. 181 e to the 5t, yes, plus C2, 10, negative 1, 1, e to the negative 4t, plus C3, 101, e to the negative 3t. It's good news to know that in these cases, it's a whole lot less work than what we were doing before, right? Remember doing the process of elimination and solving the resulting equation that was now only in one variable using our old techniques. So why would we do that? Okay, well, we've only looked at the easiest case, so it's not all rainbows and roses here. So let's kick it up a notch, shall we? What about repeated roots? Or I should say eigenvalues. It's roots in the sense that, remember, the eigenvalues come from the characteristic polynomial for the matrix A minus lambda I. You take the determinant of A minus lambda I. So what about repeated eigenvalues? Okay, so for example, consider x prime equals, I'm going to go write it in matrix form, 3, negative 18, 2, negative 9 times x. So a minus lambda I, the determinant of that, it's actually just as fast to do this by hand as it is to get my browser up and running and type in this matrix. But that's going to be 3 minus lambda times negative 9 minus lambda minus a minus 36, which you said equal to 0. So that's negative 27 minus 6 lambda plus lambda squared. Actually, that makes that a plus 6 lambda. Plus 36 equals 0. Just multiplying that out, I get lambda squared plus 6 lambda plus 9. Which factors? Lambda minus plus 3, lambda plus 3. So lambda is negative 3 twice. So this is a scenario where the eigenvalues are repeated. Now there are two possible scenarios for your eigenvectors now. The eigenvalue negative 3 could have an eigenspace of dimension 1. It could have only one corresponding eigenvector, or it could have two. If it has two, life is just as easy as before. If it has one, you now do not have enough vectors to make two solutions, to make two linearly independent solutions. So we're going to have to do something similar to what we did where we just stuck in a t last time. Remember whenever we do t e to the lambda t instead of just e to the lambda t? But unfortunately, it's not quite as simple to get something that solves the system. All right, so let me put in a note here. In general, if m is some positive integer such that, you recognize this symbol, right? Z just is integers. Z plus means only the positive integers. So those are the counting numbers, 1, 2, 3, 4, and so on. So if m is one of those, such that lambda minus lambda 1 to the mth power is a factor of the characteristic polynomial, by the way, the characteristic polynomial was like this guy right here. It's your determinant of a minus lambda I equals 0. That's your characteristic polynomial. So what I'm saying is, let's say, like in this case, that was lambda plus 3 squared. So my m up here is that 2. Oh, and I can broadcast again. I'm away from Wolfram Alpha for a little bit. So this m that I'm talking about is the 2. If that's a factor of the characteristic polynomial, that means lambda 1 is a root. It means it's an eigenvector, eigenvalue, but it also means that it has multiplicity m. Okay? So let's say that's a factor of the characteristic polynomial, and just so that I'm indicating that this is the highest possible factor, lambda minus lambda 1 to the m plus 1 is not. So it's the most number of times lambda minus lambda 1 appears in the characteristic polynomial in factored form. Then that lambda 1 is said to be an eigenvalue of multiplicity m. I just wanted to formally state what I meant when I said it has multiplicity. These repeated eigenvalues will have a certain number of repeats. So the multiplicity of lambda equals negative 3 up here is 2, right? So in the previous example, lambda equals negative 3 has multiplicity 2. So now there are two cases for when we have repeated eigenvalues. as I was referring to before. 1 is where, even though it's repeated, it has the right number of eigenvectors. By right number, I mean it matches the multiplicity. So case number 1, do this Roman numeral 1 here. Let's say lambda 1 has multiplicity m, and, fortunately, there exists, have I done the backwards e yet in here? There exists m linearly independent eigenvectors corresponding to lambda 1. Call them V1, V2, all the way out to Vn. M. Which means the general solution contains the following components. It's a C1 V1 e to the lambda 1t plus C2 V2 e to the still lambda 1t. Notice how the lambda stays the same because it's repeated. But if you've got independent eigenvectors and you've got m of them, then here's part of your general solution. It's the part that goes with this lambda. So that's the easy case. We'll do an example of that. And then there's the messy case. What if it doesn't? Okay, so here's a possibility. Let's say lambda 1 has multiplicity m, and there's only one eigenvector. Actually, there's a third case, which is a combination of these two, but we'll save that. Actually, I may not even refer to that. We'll do the general case of the worst case scenario. Lambda 1 maybe is repeated, but only one eigenvector goes with it. What do we do when that's the case? Well, we have to build all of the linearly independent solutions, right? Up here, like this right here, you don't have to write this on here, but in fact, I'll even do it a different color. Write it in red. This actually is m linearly independent solutions combined together. Each one of these things that I underlined is a solution to the homogeneous system, and it's independent from the others because the V1s are all, or the VIs are all independent of each other. So there's a solution, there's a solution, there's a solution. Like x1, x2, all the way out to xm. I need to create an x1 through xm down here, but all I've got is one V to work with. And so in order to do that, I'm going to spare us, just more for lack of time than anything else, the derivation of this, but the way that it works, actually I'll derive one in a very simple case for you in a minute, but in general, here's what it looks like. Your x1, let me go ahead and say, by the way, then the fundamental set contains the following vectors. x1. The first one's easy. It's and I'm going to use a a V11 notation. E to the lambda 1t. And there's an x2, which will be a V21 t e to the lambda 1t plus V22 e to the lambda 1t. Now, we have no idea what these v's are yet. And where they come from, we're going to have to derive in a moment. x3 is another vector, 3, 1, and it's going to be multiplied not times t, but actually times t squared over 2 e to the lambda 1t plus a v32 t e to the lambda 1t plus a v31 e to the lambda 1t. Dot, 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 all the way out to an mth one, which would be a vm1, and this is going to be t to the m minus 1 over m minus 1 factorial e to the lambda 1t plus vm2 t to the m minus 2 divided by m minus 2 factorial e to the lambda 1t plus all the way out. And notice how my power is just decreasing, right? I had just a 1 here, I had a t and then a 1, now I've got a t squared over 2, a t and a 1, now I've got a t to the m minus 1, t to the m minus 2, all the way down to 1. So I'll have a vmm e to the lambda 1t. Where the v, I, j are column vectors, and later we'll discuss how to find them.
Was that vector, that x3 is supposed to go v31, v32, v31?
3, 3.
3, 3, okay.
Thank you. So x1 only has 1 term, x2 has 2 terms, x3 has 3 terms, xm has m terms. And what I'm doing is I'm creating a combination where the actual functions times these unknown vectors at this point are these polynomials times e lambda 1t. But they're specifically t to a power over that power factorial. It can be shown that when we choose them of this form, we can always find these so that these are linearly independent and they're solutions to the original system. So we hope for either distinct eigenvalues that are real or that we have multiplicity, but we've got the eigenvectors that match the multiplicity. If we don't, we've got some work cut out for us, but we're not without hope. We can still figure out how to do it. So let's do one example like case 1, and then let's talk about what case 2 would look like. So example, let's say we've got x prime is 1, -2, 2, -2, 1, -2, 2, -2, 1 times x. So again, what I would do, jump over here. Let's go type it in. You can just watch me. Unless you want to do it, you can do it yourself. By all means, have fun. Go to town. 1, comma, -2, comma, 2. -2, comma, 1, comma, -2. 2, comma, -2, comma, 1. Type it in right. 1, -2, 2, -2, 1, -2, 2, -2, 1. I get lambda 1 is 5 with corresponding eigenvector 1, -1, 1, and then I get a repeated eigenvalue, right? Eigenvalue -1 is repeated, so it's got multiplicity 2, and if I look down here, I've got an eigenvector for it twice. In a moment, I'll show you an example of what it looks like in Wolfram Alpha if it's repeated. That is, you don't have a full number of eigenvectors, right? So again, it's possible to get a repeated eigenvalue, but only end up within 2 eigenvectors, right? So lambda 1 goes with v1, lambda 2 goes with v2, and lambda 3 goes with v3. But it's possible to get a lambda 2 that's -1 and only a v2, and then there's no extra v3 to go along with it again. Okay, but in this case, you can immediately write down the answer. There's no work to be done. Then you immediately know that x is c1, and then you do the first eigenvector, -1, 1, -1, 1, e to the 5t plus c2, -1, 0, 1, e to the -t, plus c2, c3, 1, 1, 0, e to the -t. So notice how both of these have e to the -t, but because they're eigenvectors, the column vector that's in front of them are linearly independent, then these two solutions are linearly independent from each other. Done. Easy. All right, so I'm going to start by stating the example, but I'm going to have to do some more work in the middle of this to give you some formulas to work with. But let's look at one case that's not so easy. Is everybody okay with that one? All right. All right, here we go. X. We'll do a 2 by 2. 3, -18, 2, -9 times x. And this is a prime, sorry, right there. So typing that in, 3, comma, -18, 2, comma, -9. Okay, so results. -3, -3, v1 is 3, 1, v2, it says 0, 0, but that's its way of telling you there is no v2. Because in order for an eigenvector to be an eigenvector, it has to be non-zero. Exactly. So, since that's 0, that's not 1. All we get is one eigenvector out of this matrix. Okay? So, lambda 1 is equal to -3, multiplicity x2, and we only get one eigenvector, v1, which is 3, 1. Okay, so for a second, scroll back up here and realize what that means we've got to do is we've got to find an x2 that looks like this. We need to know, how do I find this and this that makes x2 be a solution to my system? Okay? So let's take a little break here. And let's do a simple version of case 2. Okay? Namely, lambda 1 has multiplicity 2, and only v1 is an eigenvector. Okay. So in that case, your x1 will still always be, even though I used v11 in the notation, turns out that v1 is the part of your first solution, v1 e to the lambda 1t. Vector right there. All right, now for x2, here's what I suggest that we do. We're going to use the same v1 here, t e to the lambda 1t, plus, and I'm going to use I'm just going to put another variable in. I'm going to call it p for right now. Actually, tell you what, can I call it v2? That works. We don't know what v2 is yet, but let's find it, okay? v2 e to the lambda 1t, okay? So the question is, how do we find v2? Answer, plug it into the system. That is, I'm going to plug this whole x2 into x prime equals ax. And do some just matrix algebra to solve for this v2. Make sense? I know what v1 is. v1 is the solution to this, right? v1 is an eigenvector that corresponds with the eigenvalue lambda 1. Okay? Now I want to find v2 using this x2 plugged into this equation right there. Right, so I'm doing that. This is the guy that I'm actually plugging in. Okay, so x2 prime. First of all, let's just take the derivative of this, see what we get, and then set it equal to a times x2. So the derivative of this, vectors, these are just constant vectors, so they can be treated as constants. So you can use your algebra for derivatives that you know. Meaning the derivative of sum's derivative, you can pull constants out, that kind of stuff. Okay, so what's the derivative of t to the lambda 1t? Use product rule. So you get first times the derivative of the second, which would be a lambda 1 v 1 t e to the lambda 1t plus the second e to the lambda 1t times the derivative of the first, which is just v1 e to the lambda 1t plus now the derivative of this, which would be lambda 1 v2 e to the lambda 1t So this we set equal to a times x2 v1 t e to the lambda 1t plus v2 e to the lambda 1t. This is just x2 prime equals ax2. Like that. All right, so what I'm going to do, I'm going to distribute this, which gives me a v1t e to the lambda 1t plus a v2 e to the lambda 1t. And then I'm going to subtract all of these to the other side. So I'm going to take this guy here, which is a t e to the lambda 1t, and I'm going to move it over to the right-hand side, and notice how those are in common, right? They both have t e to the lambda 1t. So what I actually end up with on the right-hand side now, on the left I'm going to get 0 because it's all gone, it's all moved over. But on the right I get an a v1 minus lambda 1 v1 t e to the lambda 1 t. That's the yellows. And what do I get? Let's do blues. Just the e to the lambda 1 t's have all of these together. So I'll have an a v2 minus lambda v2 minus v1 e to the lambda 1t. You with me? Okay. Now, I want you to look at this thing right here. What do you notice about him?
It's in the same form as the Eigen.
Yeah. Lambda 1 and v1 satisfy this, right? So if AV1 equals lambda 1 v1, what does AV1 minus lambda 1 v1 equal? 0. This whole term right here is the 0 vector, right? Since AV1 equals lambda 1 v1. That's the main property of lambda 1 and v1. So what you end up with now is AV2 minus lambda 1 v2 minus v1 e to the lambda 1t has to be the 0 vector. 0. I flipped this equation around, but it's just this guy here equals 0. And now since e to the lambda 1t is never 0, the only way for this to be 0 is if AV2 minus lambda 1 v2 minus v1 equals 0. So move this over here, because v1 we know, and then I'm going to factor out the v2 here, which is the unknown. This becomes a minus lambda 1I times v2 equals v1. Just add v1 to both sides, and then remember when you factor out a v2 from both of these, I can't take a matrix minus a scalar, so that's where I stuck that I in right there. Identity is the same. Multiplied in, whether it's there or not. So this right here is what we solve for V2. And there's some nice symmetry here in case you don't notice it. If you remember, the way that you find V1, A minus lambda 1 V1 was equal to 0. You use that to find V1. That's what the computer is doing when it finds an eigenvector. Then you do A minus lambda 1 I times V2 equal to V1. You just put in your solution on the right-hand side and then solve the new system. Now, you may not really recognize what's going on here, but this is just a matrix system. So let's put some numbers in so we can put some meat on the bones here and really see what this looks like in an actual problem. But this is the key idea right here, is that these are what x1 and x2 look like. V1 is the eigenvector. Now to find V2, you solve this system. That is, you take the matrix A minus the eigenvector, eigenvalue times I, times V2, and put on the right-hand side the V1. And then once you've solved for V2, plug it in here. Now you've got your two solutions. So above, I'll go and scroll up, our lambda 1 was negative 3, our V1 was 3, 1. So we have lambda 1 is negative 3 and V1 is 3, 1. Okay. And by the way, A is, just for reference, 3, negative 18, 2, negative 9. So x1 we already know. That's V1 e to the lambda 1t. So 3, 1, e to the negative 3t. Now find V2. And V2 is A minus lambda 1 I times V2 is V1. V1 is 3, 1. What's A minus lambda I look like? Minus a minus 3i. That's what goes right there. So remember 3i is 3 times 1, 0, 0, 1. So I'm adding 3 to the diagonal. So you get 6, negative 18, 2, negative 6. Agreed? Mm-hmm. Don't get surprised by this fact. This actually will always have infinitely many solutions. It's required, it's guaranteed to have infinitely many solutions because A minus lambda I is always singular. Its determinant is 0. When the determinant is 0, there are infinitely many solutions. So you will actually have infinitely many answers. V2 is just any one solution of that. So if I wrote this as an equation, right, it looks like, I don't know, what do we want to call it? 6, I'm going to call it A. If V2 is like AB. 6a minus 18b equals 3, and 2a minus 6b equals 1. All right, we're looking for an AB. And you can take any skill that you have to be able to solve that kind of system, do it by hand, by substitution, plug it into Maple, plug it into Wolfram Alpha, or in this case, it's really easy to do by hand. But do you notice that the second equation is just 3 times the first equation, or the other way around? The first equation is just 3 times the second equation, right? So this actually is equivalent to just the equation 2a minus 6b equals 1. You can find a general solution if you want to, or you can do it the easy way, which is just pick some values for one of your variables and find the other one that goes with it. Find any solution. I only need one solution to be my V2. So this system is equivalent to just that one equation. So let's say let A be 0, which means 0 minus 6b equals 1, so b is negative 1/6. So we'll let V2 be 0, negative 1/6. So any solution to this equation is now a good choice. All right, now that means x2 is, go back up here and look, peek if you need to. It's v1, which is your eigenvector, t e to the lambda 1t. So 3, 1, t e to the negative 3t, t e to the lambda 1t, plus 0, negative 1/6, e to the negative 3t. Which means then your general solution is a c1x1 plus c2x2, or c1 times 3, 1, e to the negative 3t. There's your x1, plus c2. Now your x2 is 3, 1, t e to the negative 3t plus 0, negative 1/6 e to the negative 3t. So that's one form of your answer. Just, by the way, keep in mind that any solution up here, any A you would have chosen may have given you a slightly different V2. In fact, if I had chosen, I'm going to peek at something real quick. Say I chose A is 1/2. Just out of the blue, why did I choose that? I don't know. Actually, what makes more sense is, what if I chose b equals 0? Then what does that mean up here? Another option. You get 2a equals 1, so a is 1/2. So what would be the vector in that case? 1/2, 0. So if I put a 1/2, 0 here, I've still got a fundamental, or I guess a linearly independent solution from x1. The reason I chose this one is, and I don't know if you saw it, It's right there on this page. It's something called the corresponding generalized eigenvectors, which means that whenever you've got repeated eigenvalues that only have one eigenvector, Wolfram Alpha goes ahead and returns for you these other vectors you need to be able to build a general solution, and they're called generalized eigenvectors. So like up here in this, where was it? Case 2, where there were like all these vectors, it's going to give you all of these that you need straight out of Wolfram Alpha, which is what Maple doesn't do, and it doesn't do corresponding generalized eigenvectors very easily anyways.
So is that mean we can use them instead of going through House
I want you to know where they come from, so you need to do one by hand, but yes, you can do them straight off of Wolfram Alpha. I mean, the most important thing is that you know this box right here, that you know the V1s are the eigenvectors, and then V2 would be the next corresponding generalized eigenvector. If you had 3 of them, then you would have to deal with 3. In fact, let's do that one. In 3 minutes I can do it, thanks to Wolfram Alpha. Let's do no, I can't do it. I can't do it in 3 minutes. Sorry. I have too high, lofty aspirations. It'll take me longer than that, because I need to talk about where the equations for the generalized eigenvectors come from. So I got to stop there, and we'll come back and we'll do a 3x3 first thing. It'll be a good way to refresh where you're remembering, what we have done, so I don't just start in the middle of something brand new. We can go back and review. So we'll stop there and then go back up and do the 3x3 example that I've got in my notes. Now let me point out that we're still only about 2/3 of the way through all the possible situations, because we've talked about repeated, we've talked about distinct. What we haven't talked about at all are complex. When you have complex eigenvalues or complex eigenvectors. And what do we do when we don't want i's in the solution, but the i's show up in the roots?
I bet we use trigonometry.
Yes. And actually doing the eigenvalue part's easy. It's the eigenvector part that's, now you've got eigenvectors that have complex numbers in them we got to worry about.
Did you free us?